Okay, welcome everyone to the DDPS webinar series. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you're welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Greg Beroza, who is the Wayne Lowell Professor of Earth, Energy, and Environmental Sciences in the Department of Geophysics at Stanford University. His research concerns earthquake science broadly, with a focus on developing techniques for analyzing seismograms to understand how earthquakes work and to quantify the hazards they pose. Since 2007, he has been first deputy director, then co-director of the Southern California Earthquake Center. Since 2013, he has also been co-director of the Stanford Center for Induced and Triggered Seismicity. His current research includes using ambient field measurements for ground motion prediction, developing data mining and machine learning methods for earthquake detection and characterization, and understanding the systematics of induced slow and intermediate depth earthquakes. He has authored over 200 peer-reviewed scientific journal articles. Dr. Beroza was an NSF Presidential Young Investigator, has been fellow of the AGU since 2008, and recipient of many other numerous awards. Today, Greg will talk about towards complete machine learning-based earthquake monitoring workflows. Please enjoy his wonderful talk. Now, without further ado, let me pass the baton to Greg by asking one random question as usual. Today's random question is, what is your favorite things to do other than research?
Other than research, my favorite thing to do is probably play guitar.
Oh, nice. You like music. I love music too.
I love music, yeah.
Wonderful, wonderful.
Okay, well, thank you, Young Soo, for that very generous introduction, and thank you to the audience for attending the talk. So as Young Soo said, I'm going to be talking about work in seismology, which is what I do, using methods of AI, almost entirely neural networks of one sort or another, for improving earthquake monitoring. And you see at the bottom of this first slide a long list of, or a lot of symbols of different organizations that have funded this work at different points in time. So I want to make sure to give credit to them. So I gather this is somewhat of a broad audience. So I'd like to first make the case for why earthquakes are an interesting target from a data science point of view. So one thing that makes them interesting is that we have a lot of data. So we don't know when earthquakes are going to happen ahead of time, unfortunately. So we have to be measuring the motion of the ground all the time in order to detect them. So we typically sample at 100 samples per second, and we do that 24 hours a day, 365 days a year. Our networks range from isolated sensors of one to many tens of thousands of sensors. We have very many small earthquakes. As we'll see, they follow a power law, such that for each magnitude unit increase, we get 10 times more earthquakes. Our data has been digital since 1990, and we've saved all of it since about 2000. So there's a lot of data to sift through. The signals are interesting. They're broadband. They have certain characteristic attributes. Adjacent events that occurred near one another have similar waveforms, and that's actually very important for what I'm going to be talking about today. Our noise is also interesting. So we have noise all the time. It has all sorts of sources, from cultural, that is people moving around or driving around, to the oceans, the atmosphere. All these things couple into the earth make our readings noisy. It's non-stationary. Most of what we record is noise, actually, and we can use it for certain purposes. Earthquakes themselves are not completely understood, so there's a scientific frontier. That makes them interesting. They tell us about processes that occur deep in the earth and are otherwise inaccessible. So seismology is, you can think of it as a sort of form of remote sensing. And then, of course, earthquakes are threatening. They cause great damage and loss of life when they occur, if they occur in the wrong places. So it's important to understand them as best we can. So an example of a destructive earthquake sequence that occurred over the past decade plus is in central Italy. The Apennines of Italy are slowly spreading apart, and that manifests as occasional earthquakes. And in 2016, 2017, there was a series of earthquakes, the magnitude 6 Amatrice earthquake that killed over 300 people, followed by other damaging earthquakes, including one near Norcia. And this earthquake sequence happened over a period of over 10 years. And that sort of behavior where you have not just one earthquake, but a sequence of earthquakes is characteristic of the Apennines. And so here and everywhere else, we'd like to understand earthquake sequences better. We'd like to be able to forecast the likelihood of future events better than we can do right now. And so the premise of this presentation is that we can use methods of AI to do this earthquake monitoring better than we do, and that better monitoring will give us a deeper understanding of earthquake occurrence. So shown on the left is sort of the standard earthquake catalog. It's focused on the Amatrice main shock, which is shown there with the yellow star. Each one of these red and blue dots represents a small earthquake color-coded by time over a 1-year period, going from red to blue. And the topography of the Apennines is shown in the background. And this is an inset. It's a zoom in on this overall decade-plus long sequence. What's shown on the right is the catalog we were able to develop using the methods of mostly deep learning. It has a magnitude of completeness where we record all the earthquakes down to about magnitude 0.5. And because there's so many small earthquakes relative to large earthquakes, the information density goes up by an order of magnitude. There's I think that it's 13 times more earthquakes on the figure on the right as compared to the left. And so we're able to generate these catalogs using exactly the same data, but just treating it a little more carefully, if you like. And so what I'm going to explain or try to explain during this talk is how we develop these better catalogs. I'll call them deep catalogs, or sort of a shorthand. And then towards the end, I'll show some applications that demonstrate the sort of things we can learn from these deep catalogs. Our data are seismograms, so that's their digital recordings of the motion of the ground. Typically, we measure velocity, not always, but typically. Ideally, we measure the full vector, so the 3 components of velocity. I already mentioned that it's continuous, and our sensors are arrayed in networks of up to tens of thousands of instruments. One nice thing for machine learning, for supervised machine learning, for example, is that we have already existing earthquake catalogs that have very large labeled data sets. They're almost ready to go, that can be used for training deep neural networks. But these catalogs have issues. So I'll just illustrate a few of these issues. Sometimes we have a set of waveforms. So this is a seismogram here. This is time increasing from left to right. This is 6 seconds of record. It's 100 samples per, or 1,000 samples per second on this scale. And this is the motion of the ground in digital count. So here's an example where we have the catalog says there's an earthquake, but there actually isn't anything in the waveforms. So those sort of blunders creep into catalogs. A more common thing really is that here we have an earthquake. So there's a very impulsive P wave followed by an S wave. That's sort of the characteristic signature of local earthquakes. But there's a smaller earthquake back here later in the record. And there are a lot of these smaller earthquakes because of the power law behavior. These are the events that are missing from the catalog that we'd like to find. So having this, if we were to consider this to be noise, that would be exactly wrong, because those are the things we're looking for. So we have to be careful of having, say, missing labels in this instance. And during earthquake sequences like the one I showed, there might be a lot of these earthquakes. So here's a single earthquake that's in the catalog shown with blue, but there are maybe a dozen or more earthquakes following it that are not present in the catalog, and we absolutely would not want to treat that as noise. And then sometimes they're just errors in the catalog. So here's an example where the onset of the earthquake is supposed to happen at the blue. That's what the catalog says, and yet the real beginning of it is a second or so earlier. So Mustafa Musavi, who was a postdoc and a research scientist, now a research professor at Stanford, also at Google, put together a large global data set of seismic signals for AI. It was based on earthquake catalogs, but he did a whole lot of quality control, added many labels, put it in a data science friendly format, together with some sort of introductory seismology, such that it could be used by data science practitioners who weren't seismologists, but who might be interested in seismology. So that's out there. This is published in IEEE Access. If anybody's interested in exploring earthquake signals, we'd love to have you involved. Okay, so what's the earthquake monitoring task? Well, we're listening, right? We're listening with our sensors to the motion of the ground. And so here's an example where we have 6 stations. They're shown in map view here schematically with the black triangles. We have 2 earthquake sources, one shown in blue, one shown in yellow. And these are the waves that we record. Now, when we record these waves, we don't know where the earthquakes are. We don't even know how many earthquakes there are. So our job is to figure out from these wiggles where the seismic waves are and how many events are causing them. And when we do that, then we could color in the blue seismograms for the blue events, the blue event, and the yellow seismograms for the yellow event. But we don't know that a priori. That's something we have to figure out. That process is called association because we're associating measured wave arrivals with the events that cause them. And it's really central to this problem. So how is this done? Well, the standard approach uses is called STA-LTA, or there are other characteristic function-based methods, but basically they're something similar to this, where you take a short-term running average of the squared signal. So here's our seismogram, here's the squared signal. You take the ratio of a short-term and a long-term running average. When you have an impulsive arrival, that statistic gets large, and if it's above a threshold, then we say, hey, there's a wave arriving at the station. We have to figure out what kind of wave it might be, or maybe it's not really a wave. Maybe it's some local noise source. But that's sort of the fundamental first step. Then we do that association that I talked about, and if it's a real event, then we try to figure out where it is with a form of triangulation based on the wave equation, and then characterize it. So calculate its magnitude. So that sort of seems like an easy task, a straightforward task, but it's more like a lot of things. It's more difficult than it looks. So here's an example. These are seismograms. Each one of these is 10 minutes long now. And so these are offset. Each of these lines is offset by 10 minutes. Here's a nice earthquake. You can see it has a very impulsive first arrival. So that STA-LTA statistic will be large, and it will clearly register that event. But on this same record, there are a bunch of small events, just like before, We'd like to capture those too, but they may not be strong enough to trigger our sort of naive approach to measuring the arrival time of seismic waves. We also have cases where the earthquakes or events, as we call them, emerge from the noise, such that the LTA is large enough that the STA, the short-term average, doesn't peak up enough for them to be detected. And these are important cases. And then, perhaps even more important, is when the Earth is really active, when we have an earthquake swarm or a volcanic eruption or an aftershock sequence. The events are closely spaced in time, such that the waveforms overlap, such as shown here. This is an earthquake swarm in New Zealand. And so information is pouring out of the Earth, but our standard approach for processing these data doesn't perform very well. So that these are some of the challenges that we face. There are other challenges related to noise, but these are enough. So what I promised to talk about was a workflow for earthquake monitoring, and that's shown sort of schematically here. I'll show variations of this a number of times, but here's our seismograms recorded over many stations in a network. That's our input. We have steps of pre-processing, that's cleaning up the data, maybe filtering it, getting rid of bad traces. We pick the seismic waves, detect the events. Those are sort of related tasks. We associate the phases to events. And then once we do that, we try to locate and calculate the magnitude and other parameters of the earthquake. And our output, we do this many, many times. And so over time, we get what's shown here in sort of schematically, a catalog of discrete seismic events. Now, the usual way of doing this is that these are done in serial, so one after the other. And each time we do that, there's the potential for information loss. And that information loss is both in terms of the context, as I'll talk about, and also the thresholding. So we'll return to that and show possible workarounds that can help to avoid that. Okay, so the first thing I'm going to talk about just really quickly is pre-processing, and that's and that will be using a very deep convolutional neural network that we set to the task of differentiating between the signal and the noise. And so you can see it has many, many layers. We work in the time frequency domain, and it has this standard encoder decoder structure. And the idea is that we develop a mask of real numbers that in time frequency space passes either the signal or its complement, the noise. This is, there are many parameters to determine here. So we need a lot, it's data hungry. We need a lot of examples. And we develop these examples by recombining known signal with known noise at varying signal to noise ratios, such that we have on the order of 1 billion examples for the training data. And so that's enough to, despite the fact that this is very deep, that's enough to get a model that's quite effective. So here's our simplistic notion of a seismogram. We have, this is what we record. Y is a function of time and frequency. We have some signal, we have some noise, and we want to separate the two. And so what that might look like on a single trace is this. We have this noisy long period signal, some high frequency too, and then we have this earthquake here. So we take the Fourier transform of it, and in these examples where we have close to 1 billion examples where we know the right answer. So on the other side, we have the answer in our loss function, and we train it to learn these two things here in these two masks in time frequency space, such that when this is applied to the complex spectrum, it passes the signal and this passes the noise. And then we just inverse transform in order to get that back. That's the idea. Of course, it depends it works up to a point, but ultimately it will get defeated by noise if the noise is too strong. And so this is sort of, if you're familiar with Wiener filtering, this is sort of like that, but not quite. But it's the same sort of idea. Okay, so here are examples of it. So of its application once trained, and so this is using it on independent test data. Here's our clean signal, and I'll show a zoom in on the part of the signal we care the most about, which is the initial part of the signal. Here's our noise, and this is real noise. This isn't Gaussian band limited white noise or anything. This is, this is how the ground moved as detected by a real seismometer. Here's the sum of those two. So this is a noisy signal where we have been in control of what the SNR is, because we multiply this by some number when we add it to that. And then we ask the pre-trained neural network to recover the signal and the noise. And so this is what it comes up with. And if you look closely, you can, well, first of all, let's look here at the initial parts of it. You can see it does a nice job of recovering the shape of the signal. There's very little pre-event noise. If you look closely at the noise level here, the recovered noise relative to the true noise, you see there is some diminution or lower amplitude here. So there's crosstalk between the signal and the noise, but it outperforms other denoising methods that are available for seismology. This is looking in the time frequency space, and here again you can see the recovered. It's actually easiest to see in the recovered noise. You can see that the noise is not perfectly recovered. There's a sort of a dark area here where it's being attributed to the signal, but for the most part, we're able to recover the time frequency behavior of the signal as it was in the initial in what's ground truth. So here's just another example where this is the noisy signal. Here's what we recover from it. It's very close to the original signal, particularly the things we care about, which is care most about, which is the initial shape. Here's just another example. I could show these all day. Here we tried to trick it by not giving it any signal at all and just giving it a bunch of noise, and it's smart enough, it's seen enough noisy data to know that this, and enough signals to know that this is not signal, that this is all noise. So the recovered signal is basically, it's not quite, but it's basically flatlined. So we call this deep denoiser for obvious reasons, and it does a really nice job of cleaning up our time series. And if we apply the STA-LTA statistic, for example, to try and pick the arrival time of this wave, it basically fails on the noisy data, but once it's cleaned up, it works like a champ. So this preprocessing can make really a big difference and help avoid false detections, which can be a real problem, as shown here for these simple methods. And this just shows, this is kind of a weird plot, but it shows the recovered signal to noise ratio versus the initial signal noise ratio. You want it to be high, and deep denoiser is the red crosses, and it outperforms these other methods for separating signal from noise that are available in seismology. Okay, so that's the pre-processing part of it. Now I'm going to talk about phase picking. And so this, as was deep denoiser, Wei-Chung Zhu was the student who worked on this. He's now moved on. He's a postdoc at Caltech. But what we did here was to classify, use the seismic signals, but instead of doing STA-LTA, we treated this as a classification problem where we determined whether it was a P wave or an S wave or noise. And so here's the data. The P wave is the first arrival. S wave comes in second. It's expressed most strongly on these horizontal components. This is east-west, north-south. And we just trained it such that it would recover a truncated Gaussian distribution centered on the P wave or the S wave arrival time, depending on the wave type. So we're sort of classifying the wave type, but we're also sort of tricking this classifier into measuring an arrival time. And so it works extremely well. It gets and it generalizes well. We trained it only on data from Northern California, but we've used it all around the world, and others have too. And it measures the arrival time of seismic waves to within a few hundredths of a second. So this just shows the output. This is independent data that was not used in the training. You can see that it picks up very strongly on the P and the S wave appropriately, as it should. That's a nice, clean seismogram. Here's a seismogram that's clipped. So actually it's the telemetry system in this case no longer faithfully transmit the ground motion, but it's seen enough examples of that. It knows how to pick the P and S wave arrival times. And likewise with noisy data, even if we don't run deep denoiser, it can do quite a good job of recovering those the P and S wave arrival times. Here it's compared with a sort of standard method. So the standard method is this AR picker, and this is compared with the closest thing we have to ground truth, which are picks by expert analysts. And so what we'd like is a distribution that's narrow and that's centered on zero, because that would mean that our automated method is reproducing what the expert seismologists do. So PhaseNet does quite well for the P wave. This is 0.2 of a second here. You can see the tails are almost non-existent out there, so it's doing extremely well. AR Picker does pretty well. It's skewed a little bit late to late arrivals. You can see there's more energy in the tails here, but it does pretty well on the P wave. The P wave is the first arrival, so it's easier to pick. The S wave is not the first arrival, so it's harder to pick because there are other scattered waves that are interfering with it. But PhaseNet does quite well with the S waves as well. This is, maybe the energies. This is also plus or minus 0.2 of a second. So that's there's more energy in the tails. Obviously, there's more dispersion about the mean, but the mean again is centered right around zero. And comparing that with the sort of existing method for SPICs, you can see the distribution here is really fat. It's really skewed. This information is really not super useful. So deep learning, in this case, really dramatically outperformed other methods that don't have the ability to learn in picking the arrival time of seismic waves. So that's really important because it's foundational to the steps that follow. The very next step is this step called association, where we figure out how many earthquakes they are and which waves are associated with each earthquake. So association is figuring out what color each of these phases should be, if you like. And the question is, why is it difficult to do association? We don't know a priori the number of earthquakes. Events that are close in time, like that swarm in New Zealand, overlap. And so the arrival times are sort of tangled up with each other. Little earthquakes, and there are a lot of little earthquakes. Those little earthquakes are only recorded on a few stations, and the recording network changes with time, which complicates everything. In addition, the background noise is non-stationary. We don't know the wave type a priori, but with something like PhaseNet, we do, because we've trained it to pick the P and the S wave. So this is something we can fix. We have both true and false picks due to noise. That's something we can control. And this sequential application of picking and then locating or associating and locating leads to information loss, which we can also deal with at some computational cost. So we came up with a new approach to doing this using a Gaussian mixture model. So it treats these phase arrival times as distributions and goes through an iterative soft clustering, unsupervised clustering method to try to figure out how many events there are and which phases belong to what events. And of course, this is iterative, but it converges quite quickly. It has some advantages over this process has some advantages over standard association algorithms. We built into it the ability to pick, or the ability to use, both P and S waves. So that's something we don't have to solve for. That's very helpful. And we use some amplitude information as well, which allows further resolution of ambiguity when there are multiple events. Okay, so just an example during a very intense earthquake sequence. This is the 2019 Ridgecrest, California aftershock sequence. This is 300 seconds of record. What's shown here, each one of these small circles represents a seismic phase measurement, and the pluses represent events that we've been able to associate compared with two other studies of this earthquake sequence. The Southern California Seismic Network, the center catalog, has 3 events during this time. We have about 10 times as many. We have about 50% more again than Ross et al. 2019. That's not necessarily better, because it's possible to have false locations or false associations here too. The point in showing this is that it's very good at finding multiple events that are closely spaced in time, which is something that we wanted to be able to do. Okay, so to this point, we've treated each of these tasks individually in a sort of modular way, but it's because these tasks are related, it's possible to combine them. So we developed a method that we called Earthquake Transformer. We published a year and a half ago, that has a attention mechanism, has a recurrent component to capture the sequencing of seismic phases, and has a convolutional component to capture the features of the waveform. And what it does is it doesn't just pick the phases, but it also detects the event waveform that they occur within. And that waveform context is helpful. So here's what the network looks like. Just like PhaseNet, it has 3 components of data in. The pink are the convolutional parts. This is the recurrent, the yellow is the recurrent part, and the global and local attention mechanisms are here for, in this case, detecting the output is the duration of the waveform, as shown here, and phase and output similar to PhaseNet, a P and an S wave arrival time within that waveform. So that context allows us to estimate the arrival times a little bit better than PhaseNet does, at least in the tests that we've carried out. Another kind of context is the context of the network. So up to this point, we've treated seismograms one at a time, or 3 components at a time, but one station at a time, and we haven't really exploited the fact that nearby instruments should also record waves if another that is, nearby instruments should record the same waves with perhaps some time lag. So this is shown here in what's called a record section. This is the distance from the earthquake, and this is this is time. And what you can see is that there's a set of wiggles that increase, the arrival time increases. We call that move out, with distance from the event. Now, if you were looking at an individual one of these seismograms, you might be hard pressed to say, I think the P wave is arriving right about here. But if you can see what's happening in the nearby stations, you can do a much better job. So that information is really useful, and that's what we'd like to be able to use, both to determine that where the P wave is, say, and where the S wave is, it's sort of here, and that there's an earthquake here. So the methods I've shown so far, they just detect the waves, threshold that information, and then try to figure it all out, where the events are. But this thing we call EQNet, which has multiple neural networks, tries to sort of do all of that at once. So the idea is the input data is no longer from a single station or single sensor, but it's a network or an array of instruments that are distributed across, say, Northern California. We have a feature extraction network that acts on the array rather than the individual seismograms. And from that, we train a set of neural networks that pick the S wave and the P wave, and then and sort of crudely localize the event in space and time. And so that looks something like this. This is a depiction of the feature space. Here's data. Here's the individual P and S wave picks. And here's our localization in the origin time, which we don't know ahead of time, and X and Y, or if you like, latitude and longitude. Now, once we have things localized and we determine how many events there are, they're well developed algorithms for getting very precise locations from them. But getting to that stage is sort of the key. Okay, and we've applied this to the Ridgecrest earthquake sequence, and it performs comparably well to other deep learning based methods. I think ultimately this method or something like it is going to prevail because it has, I should have mentioned when I was showing this, we train all of this part of it simultaneously. So these neural networks have all the information available to them all the time. We don't sort of threshold and then move on. Okay, so I think ultimately a strategy like that's going to prevail. Now, there's a lot of processing involved here, and nearly all of it, actually all of what I've talked to you about at this point, is embarrassingly parallel. So we've developed a workflow that takes advantage of that. We call it Quake Flow. It's set up to run in the cloud. It's deployed in Kubernetes, so it should be platform independent, and it should take advantage. Should have good scaling properties, and it can be used in sort of two modes. One mode would be to analyze very large archives of data that we have for, say, order of a decade or two. That's looking backwards, but it's also fast enough that it supports streaming, so it can be used for real-time or near real-time processing with a minimal latency. And I should say that so all of this part is embarrassingly parallel, and then we have this add-on here. This is a precise relative earthquake location method called Hypodd. It's for those of you who are astronomers or are familiar with astronomy, it's equivalent to adaptive optics, but applied to seismology. So that's not embarrassingly parallel. So that's really sort of tacked on to this. But anyway, it runs quite quickly. So looking at 70 stations worth of data for 3 years continuous for Puerto Rico. We ran this with PhaseNet and with the associator that I described on it. And I was worried about the cost of the cloud because like most people, I'm new to the cloud, but it only cost us $40. So that was quite reasonable. And we found 7 times more earthquakes, close to 150,000 earthquakes than were previously in the earthquake catalog. So that's a real bargain. And we're able to see much, just like with Italy, we're able to see much more detail. So this is from a recently published study in Seismological Research Letters. We have many more earthquakes and much better definition of the Gaiania Rift, which is this GR here, and then the Punta Montavo fault shown there. So we get 7 times more earthquakes, and we should be able to do much more with them. Same story for Hawaii. So we ran Quakeflow in Hawaii. Just for the 6 months recently, we get over a factor of 10 more earthquakes than in the standard catalog. So this is the histogram of the number of earthquakes with time. Blue is what we find. Orange is what's in the standard catalog. There are all sorts of interesting things here. There are deep events under the actively erupting Kilauea caldera, deep events under Mauna Kea, shallow events along the erupting rifts, or recently erupting rifts. And then there's some enigmatic deep events such as this one, which I'm not aware that anyone has seen before. These are deep events, they're color-coded by depth, that stretch from under Kilauea to the northeast. So this is not during the most active part of the eruption, but we plan to process the entire eruptive episode, and we're going to find millions of earthquakes. I'm certain, and we'll be able to get a better understanding, I suspect, of how they're related to eruptive activity. So let me shift gears to some of the things, to describe some of the things that we've learned from these deep catalogs. So this is work done by current grad student Young-Soo Park. He's applied PhaseNet to in multiple ways. In this case, he's looking at a little over a year of data. He detected, or he was able to locate precisely almost 100,000 earthquakes. He detected several times that many, but we didn't have enough data to locate them accurately. But what he was able to find was, and this is in central Arkansas, a line of events that defines the Greenbrier fault. These are thought to be related to deep disposal wells, and those wells are shown here with the numbers 2, with the hexagons. 1, 5, and 2 are the important ones. And then, excuse me, these colored seismicity, those are due to hydraulic fracturing or fracturing, and or fracking. And what Young-Soo was able to show was that this sequence on the main Greenbrier fault, where most of these earthquakes are, was actually 2 sequences, and that the wells involved in them is thought to be wells. Let's see here. Thought to be primarily wells 1 and 5. Probably well 2 was involved as well. So what's shown here, this is a cross section of the plot going from south to north. Here are the 3 injecting wells. The seismicity started near wells 1 and 5. And so those were the ones that were implicated in the entire sequence. And each one of these red dots represents a small earthquake that Young-Soo was able to detect and locate. And so it's perking along here. We're now in October 2010. In February 2011, the sequence, a second sequence actually started here and ruptured back progressively over the fault back towards these first 2 disposal wells. So this second sequence is not something that was seen before, despite the fact that it was studied by many investigators, including us. And you'll notice there's a big circle here. This was a large event, a magnitude 4.7 event that led to the very expensive shut-in of wells 1 and 5. Well 2 kept on pumping. It's not clear that was the right decision, policy decision. If you had this catalog, you might have decided to shut down well 2 and well 5, or perhaps something different. Anyway, but the point is that this sort of information would have been extremely useful to have in real time, and we could do that now. We couldn't back in 2010, but we can do that. Other things, another thing we found out from this is that once we get sort of fill in all the dots for the earthquakes, we see a very characteristic pattern. So this is a space-time plot. This is now a still plot. This is latitude on this axis, and this is calendar time from left to right. And each one of these dots, of course, are seismicity within this gray population. And what you see are, if you look closely, are these arc-shaped structures, or parabolically shaped structures that occur over many scales, from the largest scale to these sort of small scales. And this is the sort of characteristic signature of a diffusive process. And there's fluids being injected here. So the natural thing to assume is that it's the propagation of fluids, or perhaps fluid pressure. this diffusivities we get are actually pretty high for actual fluid flow, unless it's completely fracture controlled. This is a zoom into some of those structures, and as usually happens when you do this, it doesn't look quite so impressive when you zoom in. But this shows distance versus time for one of these arc-shaped structures. We fit a diffusivity to it. The numbers we get are 10 to 100 meters squared per second. Those are big numbers. And so whether it's fracture controlled or it could be a seismic slip that's diffusing, regardless of what it is, if we had this information in real time, it would help us anticipate the evolution of the sequence while it was underway, and that would be super useful for regulators. So Yang-Soo has gone on to study not just 1 year, but 10 years of seismicity for Oklahoma and Kansas, where this has been happening at a very large scale. He found over 500,000 events, but again, only a subset of them were we able to relocate accurately. That's still 316,000 events. The faults here are close to vertical, and so it's easier to visualize them in map view than when the faults have some dip to them or cutting through the crust at an angle. So we see some interesting things here. So this is the Kansas-Oklahoma border. The triangles represent stations, and each one of those blue dots is an earthquake. This Nemaha Ridge here is thought to be a barrier to fluid flow, and you can see there's a clear change in behavior across it. Not much going on over here, very active over here, and the opposite of that up here. There are other features that appear equally clear, but don't have such an obvious explanation. But we'd like to work with the geologists to understand why there's this geographically variable response. It's important. And the developments of catalogs have changed over time. The original USGS comprehensive catalog had 11,517 events in it, and the Yang-Soo's catalog has over 250,000 over this. This is over a 7-year time period. So that's a factor of 23 more earthquakes than in the standard catalog. Now, part of that comes from having more stations, as these two studies do. So we were able to get more stations. I think it's 13% more stations. So it's helpful. But really, almost all of this improvement in the depth of the catalog comes from applying machine learning to the seismic waveforms. The cool thing about it is that it allows you to it allows structures that are only hinted at by the earlier catalogs to really emerge very clearly. So we can see quite clearly that there are faults with specific orientations that are at what are called conjugate angles. And that tells us something about the friction that's active on these faults, and that these faults are optimally or close to optimally oriented. So from this decadal catalog, Yang-Soo has found that most magnitude 4 and larger earthquakes, that is those earthquakes that are large enough to cause damage, occurred on structures that were illuminated by other small earthquakes before the larger earthquakes occurred. So another way of putting that is that let's see, I'm trying to remember the numbers here. You can construct what's the equivalent of a confusion matrix for faults illuminated by seismicity that either did or did not host magnitude 4 earthquakes. And what he found is that almost 90% of those events occurred on structures that could have been identified ahead of time. On the other hand, only 4.4% of those structures that were big enough to have earthquakes actually had earthquakes. So you need to be mindful of both of those numbers. Those probabilities are small, but they're as large in an absolute sense as those that the USGS uses for potential foreshocks on large strike slip faults in California. So the absolute probabilities are low, but the probability gains relative to the background are quite high and very useful. So again, if we had this in real time, and we could do that now, this would have been useful for decision making. I'll just zoom in on a few of those sequences before concluding. Here's the Woodward sequence. This box is about 20 kilometers across, so this is a big structure. It's capable of having magnitude 4 or much larger earthquake on it based on its extent, and yet all the earthquakes were smaller than a magnitude 4. There were 89 earthquakes between magnitude 3 and 4. So not all of these, in fact, most of these larger structures don't host large earthquakes, but some of them do. There's also some, this is color coded by time, there's some interesting down dip and eastward migration with time that we could try to relate to the injection history of the wells around this region. Here's a large structure that did have a large earthquake on it, a magnitude 5.1 earthquake. It has prolific seismicity. It has these interesting structures. This is what geologists call a horsetail splay. And you can see there's this suggestion, or maybe more than a suggestion, of these characteristic faulting angles called conjugate faulting. Here it's expressed even better. This is in central Oklahoma. There's a clearly preferred fault fabric. Should emphasize that these faults are unmapped. Almost all of them are unmapped. We only know about them because they're illuminated by seismicity. And here's the largest earthquake that occurred there. It's a magnitude 5.8, caused some damage. This is the Pawnee earthquake. It's actually the largest earthquake in the instrumental record for Oklahoma. And you can see this really beautiful conjugate geometry, beautiful and complex across different scales in the earthquakes involved in this sequence. So that's it for what I'll show now for the results. I'd like to emphasize that PhaseNet is available on, and the other methods, once we publish them, are available on GitHub, being used widely, nationally, internationally, and for diverse purposes, whether it's natural earthquakes, induced earthquakes on the Earth or Mars, and that there's an emerging ecosystem for AI in seismology. We're contributing to it, but it's being, the Italians have contributed a data set for AI, and there are things like the SeisBench toolbox for machine learning algorithms in seismology. The paper on that is available on archive. I think it just got accepted for publication, and there are many others. So I've become a believer in this kind of open science and the power of this sort of approach and collaboration. So I hope I've convinced you that AI-based earthquake monitoring is effective, and also worth emphasizing that it's ready to go. These deep catalogs I've been talking about are available now, and they're becoming something of a commodity. They're not so hard to generate anymore, and they're going to make seismologists' life complicated and interesting. So what we're used to are earthquake catalogs that are sort of static in time, and they're sort of one size fits all, and they're authoritative. That landscape is going to change. We're going to have different catalogs for different purposes. That's ultimately a good thing, but the field's going to have to adapt to that. And then the next challenge is to explore these deep catalogs to develop a deeper understanding of earthquake processes. I've shown some pretty simple examples of that. I think unsupervised methods in AI are probably ideally suited for that task, and I look forward to using them for that. So with that, I'll stop and take any questions that you might have.
Thank you so much for the great talk, Greg. It was wonderful. I learned a lot more about the earthquake. Yeah, and one of your students' name is very close to mine.
Yes, that's right. Yeah. So he doesn't have a U in it. He just
yeah. but the pronouns similar. Yeah.
Yeah.
Okay, if you have any questions, please unmute yourself and ask, or you can put that in the chat room. Well, the depth of the source locations it can be also precisely detected through the flow.
Yeah, so the depth is it can be determined. It's more difficult because all our observations are on one side. They're all at the surface.
Yeah.
So for things like latitude and longitude, you can surround the earthquake and constrain its location very closely. It's harder with depth because all the observations are from in a sense from the surface and the
from
same
one
direction.
side, right? Yeah. But so it's probably hard to know how precisely correct the depth estimates from your
Well,
algorithm, because you don't have the truth.
Yeah, I mean, it is hard to be sure, but as usual, when we solve these, the earthquake location problem is a big estimation problem, and it comes with a covariance for what it's worth. It's a linearized problem typically, is how we treat it, and so we have some nominal error, and there are opportunities for testing how good that error is. When we have similar earthquake sources, so nearby events, we can locate earthquakes to within meters of one another horizontally and tens of meters in depth.
Oh, wow.
So that it can be, that's precision, not accuracy. It can be super precise. Accuracy is a little harder, as usual.
Yeah. Okay. Sounds good. Okay, so all this, the real time, the workflow you guys have developed with the abundant data, I can see it will be really helpful for the decision making, whether by predicting, okay, so the earthquake is going to come somewhere, so do something. Do you have enough data from California to tell the residents in the California?
Yeah, so we're working on the data for Northern California. So watch this space. We'll have something within a year. One of these deep catalogs for Northern California. The examples I showed were for induced seismicity, where people were injecting fluids rather than naturally occurring seismicity. There are places like the geysers where people are injecting and extracting fluid and inducing earthquakes in the process, where this could be useful for decision making. But there are also decisions to be made when natural earthquakes are occurring, right? So the USGS, reports on earthquake activity and potential for large earthquakes, and that's there are methods for introducing time dependence to that, which could be interesting to pursue with deep catalogs like this.
Okay, sounds good. All right, there's a question from Brian. He asked, he said, a fantastic talk. Can you point me to some papers or resources that describe your pre-processing steps? I'm working on a different application in the frequency domain, and the noise seems to pollute our prediction. So I'm curious on tips that would help our.
So I can't point you to it. So it's you can find it with my name or Zhu, ZHU is the first author. It was published in IEEE something, I forget the name of the journal, but it's 2019. And if you look for deep denoiser, you should find it. If you have any trouble at all finding it, if it takes more than a minute, please send me an email and I'd be happy to point you to it.
Yeah.
Oh, you can look at it's on my Google Scholar page. It's has about 100 citations.
Nice. Okay. All right. Is there any other questions?
Yes, I have a question. So I'm wondering about precursors of earthquakes. I think there were some ideas that the tensions that exist before an earthquake, so they manifest themselves in piezoelectric effects. There is electric field that can be detected on the surface, or maybe from satellite. And is that something that can be used indeed?
Well, so there are claims to that effect, and there's an AGU monograph on using electromagnetic methods and temperature and things like that to forecast earthquakes. When people try to do that prospectively, that is, before the earthquake happens, they tend not to work so well. It's retrospectively that they claim to see anomalies. So I guess to this point, I'm very skeptical that those anomalies are real. If they were real, they are real, then sure, methods like this could be used to improve them, really. Yeah, so I mean, so any method where anything that involves signals, this sort of approach would be useful for.
Okay, thank you.
Mm-hmm.
Okay, sounds good. Any other question? Oh, there is a question from Artie. Great talk. Can you say something about how AI can help us build better Earth models for wave propagation?
Yeah, so that's hi, Artie. It's a great question. There are, what I've done is sort of the low-hanging fruit for AI and seismology. That is to do these fairly simple tasks. AI can be used for, and I think that's sort of would be more in line with the usual sort of talk you get here. So AI can be used for approximating simulations. So there are all sorts of ways, or approximating a PDE solution. So the wave, it could be used for solving the wave equation. It could be used, and even if it did so only approximately, it would be enough to get good enough sensitivity kernels to do inversions probably faster. Actually, if you pose the problem, it turns out that you can develop the adjoint. You can develop basically adjoint state methods using automatic differentiation, which takes advantage of the optimization that's done for neural networks. That's sort of done for you in TensorFlow, things like that. So. And there are methods for dictionary type methods for doing sparse tomography that I think are also related and highly relevant. So there are all kinds of ways, in addition to what I've just have sprung to mind here, where you could improve wave propagation and you could improve information that's needed to do wave propagation accurately in the Earth.
All right, sounds good. Is there any other questions?
Yeah, I have one question.
Yeah.
So for the strategy of training the models, you have like one strategy is training a series of models doing individual tasks and then chain them together to get the results. But then you have another strategy that to train them as a whole like a problem set that to optimize together. But also like in one sense that this optimized together may provide more constraints from these different problems. But on the other hand is that like maybe one of them will dominate the training and then affect the results. Can you say a little bit more details comparing these two strategies?
Yeah, so that's a good question, Shinkai, and it's as with a lot of things, if you get the weighting wrong of one versus the other, you'll get it will be worse than if you did them, say in this case, independently. So I what I was referring to was that sort of approach where you consider them all together is theoretically optimum. And what we've come up with to this point is competitive with other, with doing it in a sort of serial modular way. So I guess I'm pretty confident in the long term, where long term is 5 to 10 years, that an all-in-one kind of, or end-to-end, if you want to call it that, method will be superior. But it's an open question, because I haven't proved it and probably can't. Is that what you were asking?
Yep. Thank you. Yeah, I think like both these two strategies are very interesting, and yeah, I think like in the long run, maybe one will showing like more or better results. Yeah, looking forward to see that.
Yeah, and I should also add that the place to start is to, it takes some effort to develop these and to get people to use them, right? So, doing it in a sort of modular way helps people get started. It'd be harder if it were all at once, I think.
Okay, sounds good. Any other questions? Okay, well, I found the denoising paper of yours, Greg. It's titled "Seismic Signal Denoising and Decomposition Using Deep Neural Networks," 2019. Well, IEEE. So okay. So Brian said thanks. Okay, that's great. So, well, let's thank our speaker today for the great talk and great Q&A session. Thank you so much for accepting the invitation and you gave us the really wonderful talk, Greg.
Thanks. That's very kind. And thanks to everybody.
Thank you. Thank you so much.
All right. Bye-bye.
Okay, bye.